So in this video, we're going to continue on with our unsaturated hydrocarbon lesson for part 2. Okay, so for most compounds at the grade 12 level, it is fine to use the cis-trans naming system, but problems are going to start to arise when we have more complex alkenes with more substitutions. For those, we are going to use the easy naming system, which is much more inclusive of all the different types of alkenes that there can be. As a side note, you should get familiar with using the easy system instead of cis and trans for alkenes, because when you get into upper year chemistry courses, they are going to start referring to them exclusively as E to Z. It's the more accepted way of naming alkenes now, so it is a good idea to get comfortable with this system. But basically, using the easy system, it's based off of priority. So if you have an E isomer, then that means the two groups of higher priority are going to be on opposite sides. So a good trick to remember this is to remember that the E stands for enemies, and enemies are just going to be on the opposite side of each other. If it's a Z isomer, then the groups of higher priority are going to be on the same side. So similar to the cis-trans naming system, we have to include whether it is an E or a Z isomer at the beginning in brackets, and we're going to separate that from the rest of the name using a hyphen. So now the question arises, how do we determine higher priority in these alkenes? This is determined by the Can-Ingold prelog rules. So if we look at two atoms directly bonded to the same carbon, we want to see which one has the higher atomic number. The one with the higher atomic number will have the higher priority. If the two atoms are the same, so say attached to this carbon is two other carbons, then you're going to want to look at the atoms bonded to those carbons, see which one has the highest atomic number, and compare. And you're going to want to keep going down the chain until you can finally break the tie, and whichever one has the highest atomic number, again, will have the higher priority. If we happen to be comparing two isotopes, such as hydrogen and deuterium, the isotope with the higher atomic mass will have the higher priority. So if we look at this example here, we see that on the left side, we have one methyl group, one chlorine group, and then on the right side, we have one ethyl group and one propyl group. So let's look at the left side first and assign priority. Here we see that there is a carbon directly bonded to the carbon in the double bond, and we also see we have a chlorine. Now carbon has an atomic number of 6, whereas chlorine has an atomic number of 17. 17 beats 6, so chlorine is going to be of higher priority on the left side. On the right side, we see that we have two carbons directly bonded to the carbon in the double bond. They both have the same atomic number, so what does that mean? We have to keep going to the next atoms that are bonded to those carbons. In the first one, we see that this carbon, I'll write it above, is directly bonded to a hydrogen, and another carbon, while this carbon is bonded to a hydrogen, and another carbon. We have another tie, so we're going to keep going down the chain until we can, again, break the tie. So then we end up at this next carbon, where this carbon is bonded to 3 hydrogens, while this carbon is bonded to 2 hydrogens and another carbon. Since this one is bonded to a carbon, and these are only bonded to hydrogens, carbon is going to have the higher atomic number. It has an atomic number of 6 again, and hydrogen only has an atomic number of 1. Therefore, we know that this group right here is going to be the group with higher priority. So we've established the two groups of higher priority on both sides, and we can always just draw the line down the middle and see that since they're both on the same side, we have here a Z isomer. So when we were dealing with only alkanes, we saw that they were fairly unreactive since the entire structure was essentially nonpolar. But now we're going to introduce functional groups. Functional groups are groups of atoms that will determine the properties of an organic compound. So everything from their polarity to their melting and boiling points, etc., etc. But beyond that, they will also dictate how a compound is going to react. Functional groups are actually so important to organic chemistry that as we progress, they're also just going to change how our organic compounds are named. Alkanes and alkenes are a type of functional group, as they can undergo reactions at the site of their double or triple bond to form new bonds with other atoms, so they are definitely more reactive than alkanes. Primarily, they're going to undergo addition reactions. So addition reaction is when we have two reactants, react them together, and the end result is that they form one product. The first type of addition reaction is a hydrogenation reaction. So essentially we take our alkene or alkyne and react it with hydrogen gas. Now this is a pretty cool reaction because we can actually take a unsaturated hydrocarbon like alkynes and alkenes, and we can keep adding hydrogen atoms to the structure until eventually we end up with an unsaturated hydrocarbon like we have at the end. So here we have the max number of hydrogens that can be bonded to the structure. The second type of addition reaction is halogenation, which is a reaction with a halogen. So as I've written below, we have a simple reaction between an alkene, specifically ethene, and bromine gas. And through this reaction, both the bromines can be added to the alkene to form an alkyl halide. So in the last two reactions, we were adding compounds that were made of identical atoms, so they could only result in one possible product. But if we were to react it with a compound like water, there are now two possible products that could form because the bonds are no longer identical. So how do we determine which is going to be the major product in these reactions? We can determine that through using Markovnikovs rule. So according to this rule, if we were to add a hydrogen halide or water to a compound, the hydrogen atom is more likely to bond to the carbon that already has more hydrogens attached to it. Both products would form, but there would be one major product and one would be minor. However, if there is an equal number of hydrogens bonded to each carbon in the double bond, then Markovnikovs rule doesn't apply, and there is an equal chance of each product forming. So first we'll look at a hydration reaction. So in a hydration reaction, the compound will react with water and one carbon is going to receive an additional hydrogen while the other will receive a hydroxyl, which is also known as an alcohol group. It is possible that there will be a major product here, as seen in this reaction I have below. So when we look at the structure on the right here, we see that the left carbon has two hydrogens bonded to it, while the right carbon only has one hydrogen bonded to it. So we know according to Markovnikovs rule that the hydrogen atom, when the water splits, is more likely to add to the carbon with the two hydrogens, while the alcohol group is more likely to add as a result to the carbon with only one hydrogen. And so over on the right side, I've drawn both possible products, but according to Markovnikovs rule, this will be the major product, and this will be the minor product. And so the final reaction I want to go over today is a hydrohalogenation reaction, which is essentially a reaction with a hydrogen halide. So in this case, one of the carbons will receive an additional hydrogen, but the other is going to receive a halogen atom. So again, it is possible for there to be a major product. So let's look at the example here. We see that on the left carbon, there is actually no hydrogens. It's bonded to 2 alkyl groups, whereas the carbon on the right is bonded to 2 hydrogens. Seeing that, and knowing Markovnikovs rule, we know that the hydrogen here is more likely to bond to the carbon with the most hydrogens, whereas the chlorine will then bond to the carbon with less hydrogens. And so over here, I've again drawn the 2 possible products, and we now know that the product on the right here is going to be our major product, whereas the product on our left is going to be our minor product. And with that, that concludes today's lecture.